We are going to revisit the equations of motion, the context of Newton's second law, specifically the equations we had derived for the mass spring system. And we are interested on a non-homogeneous problem, specifically when the right-hand side is what we're going to call some type of external forcing given by a periodic function. So we're going to assume that x is denoting the distance traveled by the object that's attached to the spring. And so here x is a function of the independent variable time. And so we have x double prime m times the second derivative of x plus c times the first derivative plus constant k times x. And so the big deal is that this is equal now to some external forcing we're going to assume to be of the form f sub 0 cosine of omega t, right? So we had briefly discussed this before, but let's do some derivations now. So for example, if we assume that m is different from 0, which if m were 0 then would be considering some other scenario, not this one. So for a non-zero m, we divide by m in every term of this equation. We're looking at a second order linear differential equation with constant coefficients. And so now we're going to redefine these parameters or coefficients. So let's introduce a new parameter called p, here defined as c over 2m. This is, we define p in that way, so we have that's true if and only if 2 times p is c over m, which is precisely what we have here in the equation, c over m. So we're going to do a substitution of sorts. And so by defining a new parameter omega 0 in this way, then we would have that the square of omega 0 is k over m, which is also another term that appears in the equation. So let's rewrite this equation. So that means that this equation is now looking like this. The right hand side is still this right hand side is what we were calling in general little f of t, right? And we can think of the left hand side as an operator L of x. So this is basically our operator L of x equals to f of t. So we're interested in finding the general solution of this function x of t. So we really like to find a general solution x, which is of the form linear combination of x sub c, the complementary solution, and a particular solution here called x of p, which in this short notation we would say, you know, x complementary is a solution of the homogeneous problem. That means the operator L evaluated at that complementary solution equals 0, and also the operator L evaluated at the so-called particular solution will be equal to the function f of t, which in this case is a cosine function. Okay, so that's what we're going after. So to find the complementary solution, we are going to consider the homogeneous problem, which is the operator L equal to 0. We assume that a function satisfying the homogeneous equation is exponential, and this leads to in this case, the operator L is second derivative, so this is going to lead to r squared plus 2p r plus omega squared. This being equal to 0. This is the characteristic equation for the homogeneous problem in this case. So solving for r by application of the quadratic equation, finding the roots of this quadratic equation means that we have r being equals to minus 2p plus minus square root, and everything here is divided by 2 times 1. The argument of the square root is the square of 2p minus 4 times 1 times omega 0 square, right? So we can do some algebra here, and this is reduced to or simplified to minus p plus minus the square root of p squared minus omega square, omega 0 square. So that's the form of the roots. So if p squared minus omega 0 square is positive, then we have two distinct roots. Okay, so here we'll call them r1 and r2. They're not identical to each other, and they actually have a zero imaginary part. So this is what we'll call purely real, or roots that lie on the real axis of the complex plane, meaning they are purely real numbers. Now, if p square minus omega 0 square is equal to 0, meaning that p well, if this quantity is equal to 0, then we have a scenario with repeated roots. Both roots have 0 imaginary part, but then we have a repetition of roots, and in such case, the general solution on the homogeneous problem needs to take that into account. And then we may have another scenario, right? So you can see this is either positive, 0, or what happens if this quantity here is then negative. So if this is negative, what we can do is to note, we can write p squared minus omega 0 squared as minus 1 times minus 1, right? And so we can rewrite this as minus 1 times, and distribute one of those things there, and it's negative p squared plus omega 0 squared. Okay, so and in that case, this quantity now would be positive. This is now positive, which means that this will be the case in which we have two roots with non-zero imaginary parts, two complex roots. And so these roots would look like minus p plus minus square root of negative 1, which is what we write as I, times the square root of minus p squared plus omega 0 squared. Okay, so in that case, minus p is the real part, and the imaginary part is going to involve here the square root of this quantity, right? So in such case, we're going to have to write solutions in terms of cosine and sine, where n exponential, we'll see that in just a minute. So in general, we say we have these three cases, right? So if which are in summary of what we just discussed before. So we may have a scenario in which the solution of the homogeneous problem, the complementary solution, looks like C1 e to the r1t plus C2 e to the r2t, right? If there are repeated roots, then the solution looks like C1 e to the minus pt plus C2t, this is t to the 1, times e to the minus pt. And then the last scenario is a scenario that involves e to the minus pt and cosine and sine. One thing that we have to mention here is that this omega 1 now is what we consider to be square root, right, of omega 0 squared minus p squared. It's precisely the quantity that we had discussed before, right? So that's now the argument of the square root. We can rewrite in this form, and that's precisely what goes here as part of the argument of cosine and sine. One note here is that p squared minus omega squared, that is analogous to c squared minus 4 times k times m on the formulation of the model with the original parameters of the model, right? So if we say these two things are equivalent, they come out of the argument of the square root in the equation of the quadratic equation to finding roots of such quadratic, and so it's equivalent to say that this quantity is positive, as is here equivalent to say c squared equals 4k times m, right? So that's condition, the first scenario, this condition is equivalent, and the second scenario, and the last scenario, as you may imagine, is equivalent to say c squared less than 4 times k times m, right? So you can write one condition or the other type of condition, they are equivalent. So one thing we'd like to consider here, point out, is what happens if we take the limit as t goes to infinity of x sub c of t. This is the complementary solution. So one thing that will be involved in taking this limit is that in either of these three cases, we will have the limit of that function will involve, in all three cases, there will be a term e to the minus p t, where this p is a complex number with zero imaginary part, is in fact a positive real number, and so there will be an expression of this type multiplying the limit of another expression here of t, right? But it is easy to see that because of this nature, this limit goes to 0 rather rapidly, and that will dominate. So the calculation of the limit as t goes to infinity for the solution of the homogeneous problem is equal to 0. Now, since we want to also compute the particular solution, the operator equals to this function involves cosine. So we're going to say, okay, so this is what we're looking at. An educated guess would be to propose xp to be of the form as a linear combination of cosine and sine. In other words, x of p xp of t being a cosine plus b sine. So now what we do next is that we compute the first derivative of xp, the second derivative of xp, and then we evaluate that proposed xp function at the linear operator. So we need to confirm that f0 over m cosine equals the linear operator evaluated at this proposed function xp. Okay. So evaluating the linear operator at that proposed solution, after doing a few steps of algebraic manipulation and choosing common factor, we can express that linear operator as a linear combination of cosine and sine with these coefficients. So now what is left to do is to compare those. What we want to compare those is to basically 0 times sine of omega t plus this coefficient f0 over m cosine, and then we want to equate the coefficients. So this is the basis of the rationale of this method called determinant coefficients, and so we end up with two equations and two unknowns, where the unknowns are coefficients a and b. So we're comparing the coefficients of cosine, the coefficients of sine. So we have this first equation equal to f0 over m, and the second equation equal to 0. So one thing we could do is that we could, from the second equation, not the only way of doing this, but one way is that from the second equation, we can solve for b, and that expression would be in terms of a, and then we can go and substitute into the first equation and have one equation that has only one unknown, a, for which we can solve for. So in this case, b can be solved for this expression, and by going back to the first equation, right, we have a term multiplying a plus 2p omega times b. So now we can substitute that b with the expression 2p over omega over omega 0 squared minus omega times a. So by doing that, now we have an equation that has only one unknown a, and we can solve for that unknown. This is a linear equation in a. So we would obtain that a equals an expression that looks like this. Here in this denominator, we have the square of the difference of squares, which is omega 0 squared minus omega squared, right? So there are several algebraic steps here in between, which are long and, well, you have to be very patient and very careful, right? But so once we have obtained, and I encourage you to redo these calculations and convince yourself that this is the case. So once we obtain an expression for a, then we can go back and substitute that expression for a into the expression for b. And so we obtain this expression, and we can see here that there are some terms that are going to be canceling, and this expression for b becomes a little more neat and clean. So in summary, we have managed to find exactly, we proposed a solution and found coefficients for which this solution is a linear combination of cosine and sine, and so these coefficients are given here by a and b. So the particular solution is of this type, and so one thing that remains is to rewrite this particular solution in terms now of a cosine function. A cosine function in this form with a difference, and the argument has a difference, and so the key there is to define this new coefficient